So let me start off by asking you, are there any immediate concerns? Last time I checked on Blackboard to see if anybody had posted any particular questions. I hadn't noticed any. But do you guys have any immediate questions on a particular piece of material, a quiz question, something like that?
I have two questions, Professor. One is related to the quiz, six, and then the
Oh,
other one is related to project one.
okay. We want to start with project one first?
Okay, sure.
Okay. What's the question?
So the question, it just has more to do with the different data sets. I believe it was, I'd like to work with the NYC community, I'm blanking on the name of it.
Right. Health survey. Yes.
Yes, the health
Yeah.
survey.
Yeah. New York
But
City Community Health Survey. Yes.
I guess I'm just wondering how to or what how to choose the best form of data, if that makes sense, because there's so much of
Okay, yeah, it's a pretty big survey, right? So amazing they got people to sit down for. They must have had that. There's I don't know, like 100 variables or something like
yeah
8,000 people, 100 variables, and they
yeah
get
it's
people to
just
sit
really
down for an
vast.
interview. There's a description on how they perform the survey on the New York City.gov, and I'm not sure if they pay them for it or not. And I think it's a phone survey, but they must reward them in some way or another in order to get them to sit there for the amount of time that they have to interview them. But let's go over that right after the other question, a question about quiz six, because I was planning on getting into taking a closer look at how to select a particular database that you like, what variables might be useful to you, and so on. I did delete two databases already because they only had two variables in them. And one of the things that we're asking you to do is to not just do a basic research question like does this exposure cause this outcome, but also to involve another variable that might be potentially a confounder, so that you can do a simple logistic regression or a simple linear regression that includes more than one variable. Obviously, you have two variables, you can't do that. So we at least need a database that gives you that functionality. So yeah, I'm going to go over a few of the databases, and in particular that one and the North Carolina birth database in some detail. We actually give you a few different versions of the New York City Community Health Survey. And to be honest with you, I'll show you where you can find it if you want to download a more current version of it and get a little ambitious and work with that. Okay, so let's talk about quiz six. What was there on quiz six that concerned you?
Yeah, so it was questions three and seven that for the life of me I couldn't figure it
Okay,
out.
let's take a look at them. Let's see if I can figure them out. I stumbled the last time on one of these. Actually, I might go over that one again because I did manage as soon as I got offline to kind of figure it out. Okay, let's see. These is six. Let me put it in preview. Okay, let's read this. Let's go through the first one first. Let's read what these things say. Same course as the same. Oh, yeah, they're kind of associated, the first two problems, as I recall. Same course with the same grading schemes is offered to students as an online or in person course. So for the 70 students that have taken the online course, 65 students taking the in person course. The grading scheme, in fact, I'm teaching a section of each. This is not so different. I think the async course, I think has about maybe 50 students, and the in-person course, I think has about 25. The grading scheme gives each student a score between 0 and 100. I want to assess if the online version of the course is more effective than the in-person version of the course. So we have two variables here, right? We got a categorical variable or nominal variable, which is which course did they take? Did they take the online course or did they take the in-person course? And we have a numerical variable. What score did they, how well did they score in those sections? How well did they perform in those sections? And that's on a scale of 0 to 100. So I want to assess if the online version of the course is more effective than the in-person version of the course. Which of these statements about this study is correct? Well, in fact, if all we were concerned about is those two sections, we already know the answer to that because we know the mean. If the whole population is this 70 people and this 60 people, we already know which one performed better because we know the means of the two populations. Obviously, this is meant to be a sample. In other words, this is representative of all students taking this course online, all students taking this course in person, which may be thousands in a large institution, for instance. Okay, but they just randomly chose these 135 students. So, what's our null hypothesis here? Well, first of all, how do we compare to what statistic are we going to use to compare it to these? Well, since it's a numeric variable, we're going to compare it using average. So, what was the average score for the people that took the async course and the average score for the people that took the in-person course? Okay, we're going to compare the two averages. So, how do we get? So, we have two samples. We're going to compare two means. So, what test do we use to compare two means? Well, that's a two sample t-test, right? We know it's a t-test because it's comparing means. And we know it's two samples because it took a sample from one group and a sample from the other group. That leads to this second question. I won't go over which one it needs to pick. I'll leave that up to you. The same course with the same grading schemes is offered to students as an online course, in-person course. So far, 70 students have taken the online course, 65 have taken the in-person course. The scheme is pass or fail with a high fail rate, 50%. I'll mention in a moment why they said that 50%. Okay. I want to assess if the online version is the more effective than the in-person version. Which of the statements about the study is correct? So let's talk about what kind of study is this. Before we had a categorical variable, right, which was async or in person. That was our exposure, and our outcome was what was the average score that each one of the two groups got, and we compared the means. In this case, we have two categorical variables. We have the course that they took, async online, and how the outcome was, passed or failed. So if we have that kind of, how would we represent that uh, to someone if we wanted to describe that data? What would we create to describe that kind of data? What do you think? Take a guess. In other words, how would you display something like that? Right? We have two possible exposures and two possible outcomes, like a yes, no, like HIV positive, HIV negative, and IV drug use, yes, IV drug use, no in the rows, and HIV positive, HIV negative in the columns. How would you, I mean, what is that? What do we call that? Remember?
I want to say 2 by 2 table, but I don't think that's
Yeah.
correct.
Yeah, 2 by 2 table is
Oh, it
fine,
is. Oh,
right?
okay.
2 by 2 table is fine. You recognize that's the way you're going to organize it. A lot of times we call it either a contingency table or crosstabs, as simple. So if you want the statistical jargon name, it's a contingency table or crosstabs. In real life, you got it exactly right. It's a 2 by 2 table, and where you can display the information, right? Where in the upper left hand corner it's going to be the people that took the async course and the number of people that took the async course and passed. And then next to it is people that took the async course and failed. And then down below people, and so on and so forth. But you can imagine how to be laid out. Okay, so when we have a 2 by 2 table, what kind of statistical tests do we apply in order to determine if there's an association between the exposure, which way you took the course, and the outcome, whether you pass or fail? Right? What kind of test would you use in a 2 by 2 table?
Can we do odds ratio?
Yeah, bingo, perfect. Odds ratio. You can do chi-square, which would be perfectly fine, or or you can do odds ratio. The thing about chi-square is that chi-square just gives you one number and a p-value, and that p-value tells you the probability that you would get that outcome if the null hypothesis were true. So if the probability that p-value is less than 5%, it's saying that there's less than 5% that the null hypothesis is true if I got this big a difference between my observed values and that imaginary table we call expected values, right? So if there's less than 5% chance that the null hypothesis is true, we're willing to roll the dice and say, let's reject the null hypothesis and accept the alternative hypothesis, which is there is an association between, in this case, how they took the course and whether they passed or not, right? So knowing that, right? Well, why would we use odds ratio then? Well, we use odds ratio because we get the same kind of information, but it also gives us an order of magnitude. So in other words, if the odds, the odds would be the left top row, the left box divided by the right box, over the second row, the right box divided by the left box, and that would be your odds ratio. And that might come out, say, look, to a number like 2, right? So let's say the thing on top was the in-person class, came out to a number like 2. What that would indicate is that your odds of passing the course are twice as great if you took the in-person course as opposed to you took the async course, right? And if it had come out to be 0.5, what it would suggest is your odds of passing the course would be less if you took the in-person versus the async version of the course, right? So the odds ratio not only tells you, well, how do we know that there's less than a 5% chance that less than 5% chance that wouldn't be true, that the results are just due to just random chance, right? How do we know that? Well, like the chi-square value, we need to measure how likely it is we would get that outcome if the null hypothesis is true. With null hypothesis, in this case, there's no difference in the odds for async or for in-person. And if we think about it, the odds ratio, if we say there's no difference between in-person and async, that would be basically the same number on top and same number on the bottom, which would mean an odds ratio of 1. So how do we determine that it's less than 5% chance of being null hypothesis being true? Well, we calculate, in addition to our odds ratio, we calculate a confidence interval. And if a 95% confidence interval. So even though we know the odds ratio is, say, 2, we need the odds ratio to tell us, well, what's the chance that it could be 1, that 2 just came up, because we just had a funky sample or something like that. How often would that happen? Right? Well, the confidence interval tells us that we're 90, even though we think it's 2, we're 95% certain that the true population odds ratio is going to be, let's say, between 1.5 and 2.5, right, on either side of 2. Well, that would tell you that we're 95% sure also that it's not 1, because 1 is outside of that confidence interval for what we think the true odds ratio is. Now, but if that confidence interval had been 0.9 to 3.2, 1 is in there. So it's within that 95% chance that the null hypothesis could be true, that the odds ratio could only be equal to 1. In other words, no difference between the two groups. So in that case, we can't reject the null hypothesis. So you got 2 ways of doing the same thing. Odds ratio is preferable because you get an order of magnitude in addition to, figuring out what the odds are of there being a real association there. So let's read the problem. Now that I went through all that, that's not, I sense that that's not really what they're asking here, but that's good background. I'm glad you brought this up because it can be pretty confusing first time you learn this stuff. So far, something but which of the statements is correct? Okay, which of these statements is correct? So that implies that 4 of these are wrong and 1 of them is right. That, you probably heard me say this in the past, that I hate this kind of question because then you read 4 times things that are wrong and you only read 1 thing that's right. So I mean, part of the learning process would be nice if we exposed you to more right stuff and less wrong stuff, but, because you might actually remember some of these answers that are wrong. So let's look through this. A chi-square test will provide both an estimate of both the magnitude and the significance of the difference between the groups. What do you think? What did I just say about chi-square? What does it not give you?
The magnitude?
Right, bingo, right? That's it. So that's not true, right? A chi-square test cannot be used because some of the expected counts will be less than 5 students. Ah, there is
I
a
think,
little bug here in this whole thing that
yeah,
if
I think this
those
is
box,
when,
yeah, I'm sorry, go ahead.
sorry, is this when Fisher's test is used?
Yes and no. Yes,
Okay.
yes. Fisher's exact test is more like a thing of proportions. However, we're staying away from that. I think we pretty much stay away from that.
Sorry,
However,
I just saw it in one of the
no,
slides.
I'm glad you brought that up. However, you see that there's an issue here when one of those, even though it's a big sample, 70 and 65, is a big sample group. Both of them are big samples, right? Even though that's the case, we don't have a lot of confidence in the chi-square if there's less than 5 in any one of those individual expected counts, not the actual counts, but the expected counts. However, you notice they mentioned here that there's a high failure rate of 50%. That means in each of these two groups, 70, we expect maybe somewhere around 35 students to pass it. Our expectation is 35 students will pass, 35 students will fail, and 62 students will pass and 62 students will fail. So we don't really expect to get less than 5 in the expected tables for any of this stuff. So that's not true. Not true in this case anyway, right? So we can say that's false. That's not going to be the right answer. A two sample test of proportions should be used to test the hypothesis. I'm going to hang on to that for a second because you have two proportions here, right? Okay, you have the proportion of people that are in the async class that pass, and the proportion of people in the online section that pass. That's a possibility. Let's put that aside for a second, because we can do that instead of a odds ratio. We could just say what percentage of people pass in the async group. The percentage is say 42%, and what percentage passed in the other group, 52%. And we know the sample sizes. And you might remember that there's a way for us to compare two proportions, right? It's basically like a t-test, except we're using proportions instead of means. Our point values are p with a cap on it, right? The proportion of each group. And then we have our sample sizes. And we had a formula that we could use to do that. Now, they're not asking us to calculate it here. They're just asking us to give us an answer. That sounds like a possibility. A one sample test of proportions should be used to test the hypothesis. Well, no, because there's two proportions there. There's the percentage of people that in one group that pass the test, the percentage of people in the other group that pass the test. And linear regression is suitable for testing this hypothesis. You know, they came close, but they got one word wrong here. What's the one word that they got wrong here in that one?
Linear?
Yeah, logistic regression. You could use logistic regression because logistic regression gives you an odds ratio and you have a dichotomous outcome. In other words, pass or fail instead of a number, right? So if they had said logistic regression, we might have been able to say that one was correct. So wrong, 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 wrong. The only one that's left that looks like it could be right is this one. A little bit of a curveball because before I started looking at the answers, I started automatically going to odds ratio because that's what we concentrate on this course. But you absolutely can compare the two proportions to one another. In fact, let me see if I can't find. I think I posted this. I kind of like showed it in the class recordings. T-test variations. It's a Word document that I have that I use a lot. And this is like different ways you can do the t-test and the formulas associated with them. This is standard deviation. This is if we have two samples. This is two samples and two sample t-test. And this is if you assume the standard deviations of the two groups are equal. This is if you assume that they're unequal. We actually use this one, most of the time in class. We don't use this. We just take the degrees of freedom. Smaller is the smaller sample size -1. But you might remember that. But what about this one? Two population proportions using hypothesis testing. Well, here we go. We have P1 and we have the pooled proportion, which is put everybody together, 70 and 65, and how many people pass the test. That's the pooled proportion, right? And then we say that the z-score or the t-score is equal to the difference in the two proportions for the two groups divided by the square root of the pooled proportion. They didn't really distinguish here very well. Times 1 minus the pooled proportion times 1 over n1 plus 1 over, and we have all that, right? We have the two proportions, and we can calculate the pooled proportion from the data, and we can actually calculate a z-score. Now that z-score, if it's more than 1.96, we know the p-value is going to be less than 0.05. That's the critical value at z that we need to reject this null hypothesis. If it's less than 1.96, we know it's going to be greater than 0.05, the p-value. So we need these two. This is the standard error. This is the difference between the two proportions. We need the distance between the two proportions to be more than two standard deviations apart. That's basically what this formula says. And as far as once we get the z-score, once it's over 1.96, we know we can reject the null hypothesis. However, if you want to know what the p-value is exactly, you can look up in a table. Let's say the z-score comes out to be 2.41. You can look up in a table what is the area in the tails that's represented by a value of 2.41, and then they take the area in the left tail, area in the right tail, add them together because you're doing it two-sided, and that is going to be your p-value. You can also do the same thing in R. You can do it in, there's a function in Excel that you can use, norm S dist or norm S inverse, to calculate based on what the z-score is, calculate what the p-value is, and so on. So as far as this question is concerned, this is pretty straightforward, right? That's the only one that's going to work for us in this case, among the 5 choices that they give us. But you could have used, and I showed you, this is if you were going to solve it using a 2-sample test of proportions, that's the formula we'd use. Normally, though, we probably just do odds ratio. Use R, use odds use odds ratio, or use logistic regression in order to, even with just 2 variables, to get the same number as the odds ratio as we got here. But once we get the odds ratio, you also have to calculate the confidence interval for the odds ratio, which also you can do in R, or you can do in Excel, or you can do in SPSS. Okay, what's the other question? Did I answer that question first?
Yes,
Okay,
yes.
good.
Yeah, so the next question, and then question number 7 was what I had a question on.
Okay. Oh, that's the mandolin one. Okay, this is okay. You remember we worked with box plots? Box plots
Yeah.
are beautiful, right? I mean, you could look at them and say to yourself, oh, this little whisker up here going across is the highest number. This is the lowest number. The dark bar in the middle is the median, and this bar
Yeah.
in the middle is 25th and 75th. Those are really neat and easy to work with. Well, on
Right.
a violin plot, what they're doing is it's kind of like a probability density, right? So in other words, the area in here represents the number of people that are in that range for that value. Now there is, what they're asking you to do is compare this to one that we created in. Let me just move this out here so we can see it in one window. They want you to compare this to one that we created in the lab in session 6, and that's actually a pretty simple lab. We could do that really quick. Hang on a second here, and actually, then you'll see the axes. See what the axes really represent.
Yeah, it's just that when I did a portion of the lab, I thought that I saw choice B in the shape at least, but maybe I did something wrong.
Oh, you mean choice B here?
Yeah.
Weren't there three things though? Not applicable also?
Yeah, that's the part that confused me because I saw the shape of choice B, but then knew that the choices have to be 3, like you said,
Right.
Professor.
Yeah,
So,
let's do it. We're gonna do it real quick. Hang
okay.
on a second. Might as well, because I think that this question comes out quite a bit. So we might as well just give it a shot. Okay, activities. Let's see. No, I want to go into the content.
And then don't forget, I'm also looking for question number 3. Sorry, Professor.
Question number 3 was that? Oh,
Yeah,
let's do that
sorry.
first. Yeah, let me, before I go off on a tangent. Yeah, let's do that one first. Did I close that? Probably did. Activities, quizzes. Okay, quiz 6. Oops, I shouldn't have done that. Hang on a second here. Oh, well. Okay, here we go. A program is conducted to increase healthy eating in 80 people, and 80 people take part. Each participant's healthy eating score is assessed before and after the healthy eating program on a linear scale of 1 to 100. I want to assess if the program has increased healthy eating. Which of these statements about the study is correct? Okay, so now you have 80 people take part. Each person is assessed before they go through the program, the intervention, and they're assessed again after they go through the the program. So so we have two columns of numbers. We have each person. We have 80 lines on each one of them is represented a subject, and we have a number from 100 to 1, which is their score, their healthy eating score. So let's say subject number one, they went in at 60 and they came out, they learned something, they came out, their score was 80. So the difference between the 60 and 80 is positive 20, went up 20. So the next person came in at 50 and they went up to 80. So they went up 30. Next person came in at 80 and went out at 70. They regressed, they went minus 10, right? So now we're creating a third column here, if you can imagine it. That third column is the difference before and after. So in this case, we don't really have two samples. We have a single sample, but we take the readings from the same person twice. We call that a paired sample. The sample before and sample after are not really from a different group. They're from the same people, right? So we call that so what we're really interested in there is not what the person started with or specifically what they ended with, but what the difference was. Did they improve or did they not improve? So what's our null hypothesis in a case like that? Our null hypothesis is that the difference between the average difference of people scored before the intervention is same as the average score of people after the intervention. In other words, the two differences are equal. There's no difference before and after. A difference is equal to, another way you could say that is that the average difference is equal to zero, right? So you could say it, you could describe it in words, or you could just say the average difference, the mean difference is equal to zero, right? So that's our null hypothesis. Or alternative hypothesis is that the average difference is not equal to zero. They either improved on average or they got a score went up on average. Now, of course, you measure anything twice, you never got this. There used to be an expression many years ago. I'm a bit older than you guys, but back in the old days, we used to have watches. You used to wind them up, right? And no, yeah, and we used to have an expression that the man with two watches never knows what time it is because they would never keep that good time. You had to keep them wound up and stuff like that, and they would never be exactly the same. So we had that expression. Nowadays, you have digital watches. You're synced to the U.S. Naval Observatory or something like that. So everybody's got exactly the same time. So that's kind of that little axiom has gone out of vogue. So at any rate, so the point here is that if I did this again, even if the program didn't help, we're not going to get exactly zero as the average difference. We might get -1, +3, plus -10, +12, whatever. We might get some number other than zero, right? Probably be close to zero if the program does nothing, right? Most of the times we'll get close to zero. Sometimes we get a little bit further from zero, less frequently than getting close to it, right? So we want to show that the average difference we got, the average difference is far enough from zero that there's less than a 5% chance that it could be due to just random chance, not actually a real difference in the population if we applied this to the population. So
And Prof
yes, go ahead.
Professor, this would be so a one sample test of proportions, not the paired means, right?
Oh no, paired means
Oh,
paired
paired means.
paired means paired one sample test of paired. Hang on, one sample test of paired means. Now you got to me just before I got to the actual point. Now,
Oh,
what you're going to do now is you're going to do a single sample test, a single sample t-test. And single sample t-test, what you're doing is you're comparing the average difference to zero, right? So you're taking a single sample and comparing it to a fixed number, right? So you're going to
I see.
ignore the first two columns, take the third column, take the average, use that and compare that average to zero. So you have your sample size is n. You have your average difference, and you're comparing it to a value of 0. So if you looked at it in terms of an equation, it would be the average difference minus 0 on top, divided by the standard error on the bottom. And the standard error is the standard deviation of the differences divided by the square root of the sample size, which was 80 in this case.
Professor, why can't it be choice C, test of proportions?
When single sample test of proportions should be used um, because it's a numerical variable. It's not a yes no. Uh,
Um,
if it had been, you could do that if it had been, in other words, did they go up or down? And it was up or, and the outcome was up, their food score went up or the food score went down. Then you could say what percentage of them went up, and is it more than 50% went up?
I see, I see.
Right.
And
Yeah.
and
So in this case, it's
because
a numerical variable, so you have to use a t-test.
got it. Thank you.
Okay. Number 7.
Yes, please.
Okay, good. Oh yeah, we're going to do this. Oh yeah, let's take a look at this. Yeah, this. Okay, yeah, this was a really relatively quick R exercise. It was the second one, kind of like it was almost like an add-on. And I have to tell you that I don't think you'll ever see a violin plot again in your entire lives. But whatever, it is a problem on the test, so you guys have to deal with it, unfortunately. So let me see here. Okay, let's see. Go into content, and let's go to week 6. Week 6. Week 6. Okay, I think it's this lab.
Yeah, that's the one.
Yeah. Let's see if it'll start up right from here. If I got to take it out. Oop, that's encouraging. Okay. So I'm just going to, yeah, let's do this just to make sure. It's asking me if I want to update. I'm going to say no. Otherwise, it seems to be doing everything okay. The red stuff is not a big deal. Okay, so it's youth reckless behaviors, something or other. That's the name of this data set. I'm going to click on data with that in it. Since nothing happens down there, because it's just bringing the data in here. Here it is over here. We can click on that and get a look at it. There it is, and we can see what the various variables are: age, gender, grade, Hispanic, height, so on and so forth. Hours of TV watched, strength training, how many hours of sleep they get, whether or not they text while driving over a 30-day period, and so on. So I'll go back in here, and we got a little bit of a look at it, and I'm going to question mark RB. Question mark is going to open up in this window. It's going to open up the help part of this, the codebook part of this. In other words, tell us about this data set. So here it is. It selects variables from the youth risk behavioral surveillance system, and it gives us all the different variables, describes it for us, tells us what the source of it is, and so on. And then you can use Glimpse. Also, will give you a look at the first few lines of data, and the various variables that you have. It also gives you, this is important, gives you a number of rows, how many lines of data you have, how many subjects you have, and how many variables you have. You have 13 variables. That's nice because later on, if you filter it and you don't want all these variables, or you add a variable, it's easy for you to see if the filtering worked, or if you added the variable, it took away variables if you wanted to. Okay, let's skim. Okay, skim is just a quick look at the distribution of the data. In other words, it's kind of like a histogram, except that the histogram is the histogram takes the numerical variables and displays them as a quick little block histogram. Really, almost like quartiles, right? Not quite, but almost like quartiles. So yeah, we actually, in fact, percentage 25, 50, 75, and so on. So anyway, if you look at this, you can see that whatever the height is roughly normally distributed. Age writes is most of the students in here are 16, 17, and 18. They're a little bit older. Um, uh, Weight is skewed towards is more towards the bottom, and so on. And so it just gives you a quick look at what the data looks like. Not all that useful, really, but if you needed a quick look, you got it there. This might give you a little bit more information about the means and the standard deviations for the individual variables: age, height, weight, physical activity. And I believe that these are all the numerical variables. It only does it for the numerical variables. That would explain why there's only 5 of them instead of 13. Okay, so let's do our, our violin plot. So what are we going to do? Well, ggplot, we know, is going to display all kinds of different, could be box plots, could be histograms, so on and so forth. In this case, we're defining it as a geometric plot called the violin plot. That's the part that tells us what kind of plot it is. AES stands for aesthetic, and it's going to tell us the specifics of how this is distributed. On the x-axis, we're going to put physical 3 plus. I believe if we look at that in detail, that says physical 3 plus. Is that here? They don't show it here. Oh, I know what it is. It's the number of days of physical activity that they have, right? And actually what happened here is I forgot to run this line first. I got to run this line first. What we're doing is it's the number of days that they're physically active, right? That's a numerical, I guess, a numerical variable. So what's happening here is we're modifying this data set, YRBSS, okay? And we're going to take YRBSS and we're going to put it through a process. And that process is going to be mutate. Mutate usually means you're either adding a variable or modifying a variable. And the modification that we're doing is we're going to create a new variable called physical underscore 3 plus. And what's going to go into that variable is going to be the word yes or no. If for physically active for 7 days, there is a yes in that person's data, then it's going to put in the word yes. If not, then the physically active is less than 2. In other words, less than 3 days physically active. It's going to put the word in no. So if you're physically active for more than 2 days, you get a yes. Otherwise, you get a no. So in other words, we're going to get a new variable called physical underscore 3 plus, right? Which is going to have a yes in it if you're physically active 3 or more days, and no if you're not, if you're active only 2 or fewer days. So let me run that. Okay, we run that, and now if I want, I can go back here and just glimpse at this to see if anything's changed. And indeed, look, now we got 14 columns instead of 13. That's why I was saying that utility of glimpses kind of handy for that. Okay, and you can probably see, there it is down at the bottom there. I just put something in my way here. Okay, there it is. Yes, no, 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 and so on and so forth. Okay, so now we're going to create our plot. And our plot is going to be plotted on the x-axis. It's going to be 2 groups. It's going to be a group that is yes for physically active or not physically active. And there's also going to be a third group, which is some of these students didn't say whether they're physically active or not either not applicable or not available, right? And then in the y-axis is going to be the person's weight, right? What their weight is. And it's going to be in the form of a violin plot. So I'm going to click run, and it's going to appear down here. I'm going to zoom into it. Okay, so now here's what we got here. So if you look, the most frequent value, the most frequent number, the mode, right? The most frequent number of people, the width of this represents that weight. So we have a weight of, this must be kilograms, I guess. We have a weight in kilograms. Remember, there's some younger kids in here, some older kids in here, right? It's a pretty wide age range. So we're seeing that the median for all of these, right, or the mode for all of these, probably pretty close to the median also, is somewhere around, let's say, this one's somewhere around 60. This might be 65. This might be 65. We don't have none of the lighter kids, younger kids probably responded to this. We're missing a spike over here. The spike represents an outlier. a couple of kids that might be a lot heavier than the other kids. Remember, there's 13,000 kids in this survey, right? So even though it looks like a spike, maybe it's only one value, could be several values up here actually, because such a big data set. Okay, so let's put that aside and see what we compare it to. And remember, unfortunately, they didn't give you the numbers here on the side to make it a little bit more difficult to interpret it. Okay, let's put them side by side now. Let me reduce the size of this so we can get a closer look. Okay, so let's see. Don't look like number one. Doesn't look like A. Doesn't look like B. C looks like a candidate, except the highest value is the highest weight is on yes, right? Is on yes here, but it's on no here, right? So that doesn't look right. This one doesn't look right. And how about this one? This one I think is the next possible candidate here. And let's see if I can find a difference here. The one things I can see that's right off the bat is different is that there's a little bit of a variation here in this table, in this file-in plot that doesn't appear here, but does appear here. So I'm thinking that's the right one. What do you guys think?
Yeah, that looks good, Tracy.
Okay, I'm gonna since I kind of gave it away anyway, I hope I got it right. I'm just gonna take a quick look over here. Let me just see if let me get out of this. Don't save. Let me go back here. Oh, we're still on it. What number was that again? That was question.
That was number 7.
Okay. Okay, let me see why I don't see that. Eureka, that's the right answer. So between the two of us, we managed to work that out. You know, that's a terrible question. I mean, the difference was so subtle that, like, I mean, a couple of them were like, they clearly they reversed the two violin plots, and you would have said to yourself, oh, yeah, there's a difference in this distribution compared to this distribution. But those two that where there was such a tiny difference in the variation around the middle of those violin plots, that was kind of, that I would have felt better about that question if there was a more significant difference in those two plots. Okay.
Yeah.
So for you guys there are others of us here. You other guys, you have any questions that you want me? I want to go now over some of the data sets for project one and talk a little bit about project one. You guys have any other questions before I get to that?
Can we look at 6 first before?
I'm sorry, say again.
Can we look at the question 6 on the quiz?
Sure. Okay, let's take a look at question 6. Okay. Okay, question 6. Okay, let's see what we have here. Okay, I did it again. Let me get out of here before I try not to give away too much of this, right? I don't mind giving away a little of it, but I'm hoping not to give away everything. Hang on a second. Okay, good. Well, although, to be honest with you, I'm so glad you're showing up that I don't mind giving you a little extra boost. Okay, what is the chi-square value, the p-value, and the odds ratio for this table to 2 decimal places, giving the results from a case control study investigating seaweed consumption compared to no seaweed consumption on type 2 diabetes? Please note we are not using the Yates continuity correction. The Yates continuity correction, what is that? Okay, when I if you recall, the way that chi-square works is I start with a 2 by 2 table and I create another table, these are all observed values. These are values I measured. I asked 300 and 750 people, 1,050 people, whatever it comes out to. I said, 1,000 people, do you eat seaweed? Do you not eat seaweed? Do you have type 2 diabetes? Yes or no, right? I asked them, and this is the way the data fell out. Obviously, these actually represent real people, so it's always going to be whole numbers in the observed table. My expected value table, what I do is I say to myself, well, in this population, 650 people out of 1,050 had diabetes. So the proportion that has diabetes is, say, 65%, say 60%, right? So my expectation is that in the expected values table, that let's say 65% for argument's sake. So my expectations is that in this row here where there's 300 people, I would expect 65% of them to have diabetes because that's the overall rate for the population, right? That's the prevalence, right? So I would expect 65% of 300. So let's say that that's 100, let's say that that's 192.3. That's what would go in here, 192.3. And this is 750 people, 65% of them might be 501.3, and I would put 501.3 and then put whatever the difference is in the rows here to make them match, right? So the expected values table would have fractional values in it, decimal places, fractional values. However, the original table that we have can have fractional values, even though the proportions in the real population are not going to be nice, neat, even numbers necessarily. Um, we're going to have only whole numbers here. So what the Yates correction does is it takes the formula observed minus expected squared over the expected values, and it says observed minus expected minus 0.05 squared over the expected. So what it does is it adds a little fudge factor in there to include that the number 200 could really be 195.5, 199.5 to 200.1. It includes all the people. It represents all the people that would be in that range rather than anybody that's exactly 200 pounds. So that's the Yates correction. We're not going to bother with that. And most frequently, if you have decent sample sizes, usually don't bother with it. Okay, so now investigate. Please note we're not using it. Okay, if it happens to use the method using Yates continuity correction by default, which will say Pearson's chi-square test, Yates correct, then change the options to use so that Yates is not used. So R by default uses the continuity correction, but you can easily change the option. For instance, using the test chi-square equals P, comma, correct equals false, where P is your input matrix, and P is you're going to put this. You're going to put this into your input matrix. Hang on a second here. For example, R by default use chi-square test. Use chi-square test P, correct equal false. Okay, what they're telling you here is that in order to do this calculation in R, you would first take your matrix. You're going to create a matrix. Matrix is just an array of numbers, columns and rows. So in this case, your matrix is going to be, and this stands for concatenate. In other words, this just says I'm going to give you a string of numbers. Is going to be your matrix in this case is going to be 200, 100, A, B, C, D, 200, 100, 450, 300. The number of rows equals 2. By row equals true. In other words, calculate the chi-square values by row. So you're going to take all of that, which describes this array of numbers in here. It ignores what the output is, what the exposure is. It's just looking at the numbers, right? So you're going to take all of that and put that matrix into this variable called P. And then you're going to run a chi-square test that says chi-square dot test P, run it on P with correct equals false. In other words, that tells chi-square, that tells R to leave the Yates continuity correction out. Did anybody ever actually use this, or did you use? I think in the PowerPoint I think we give you a link to a online calculator for chi-square. Did any of you guys actually use the R for this?
They did give it, but I didn't use it.
Oh, okay. Oh, okay.
Yeah,
Which
I
way?
didn't either. So that was the one I got wrong. So I got the p-value right and I got the odds ratio right. It was the chi-squared that I got wrong.
Okay, let's see. I could actually do it from scratch. You want to do it from scratch? Let's do it from scratch. Maybe it'll learn something here. Okay, let's go. Let's do it from scratch. I'm going to open Excel. Okay, let's make this bigger so we can see it. Okay, so here's our observed values. Now I'm going to create another table, which is going to be our expected values, and they're going to be down here. Okay, so what is my prevalence? My prevalence is equal to the sum of all of these different things. Okay, that's 1, 10, 50. This is equal to the sum here of these two, and this is equal to the sum here. Here, okay, good. So I got 300, 750, and it all adds up to 1,000. Okay, so now I'm going to calculate my prevalence. Now, there are 650 people who have type 2 diabetes in this population, in this sample of 1,050 people. So my prevalence, not proportion, but yeah, I guess it is kind of a proportion, is equal to 650 divided by 1050. So 62% of these people have diabetes. So if that were true, if I have these people eat seaweed and these people that don't eat seaweed, that's interesting that it did that. Oh, the whole column is probably that way. Okay, so these people eat seaweed, these people don't eat seaweed. So if 61%, 62% of people eat seaweed, if we have 300 people, I would expect here to be equal to 300 times 61%, right? Or that number. And this is going to be the difference between 300 minus this. So it still adds up to 300. This is what I would have expected if they really got diabetes at that rate. Okay, now how about this group over here? Well, this group over here that doesn't eat seaweed, I'd expect them to have diabetes at the same rate of 62%. So this is going to be equal to that times 750, which is 464. And this is going to be equal to 750 minus this. Okay, and if you add it all up, it'll come up to 1,050 again. Actually, I'll prove it to you. Whoops. Oh, shit. Oh, excuse me. K equals, I should have used sum. Parentheses. And there it is. See, proved it. Okay, so now I have to calculate my chi-square value. Okay, so my chi-square value is for each one of these cells is going to be my observed values minus my expected values squared. Where is that thing? 2 divided by my expected values. All right, so I'm going to do that for each one of these cells. So it's going to be equal to my observed value minus my expected value. And I'm going to put that into parentheses. And I'm going to square it. And I'm going to divide it by my expected values. So for that, so it's 2 cells, I get this number. So now I'm going to just copy this down, and it's just going to move this down from here to here and this down. The formula is going to be copied down. And for this one, I get that. Now I can copy it across to that formula, and I get that. And my chi-square value is, I can't draw it here, but sum of these values, these 4 values. So my chi-square value is going to be equal to the sum of all 4 of these. Like Greek letter sigma, capital sigma, is going to be equal to 4.038. That's my chi-square value. Now, what is the probability I would get that? Remember, if my chi-square value, if there's not much difference between my observed values and what I had expected, then the differences are probably just due to chance. But if there's a big difference between these two groups, right, then that these two tables, then there's less of a chance it's due to chance, and more likely that it's not due to chance. So what does that p-value have to be for me to reject my null hypothesis, which is that there's no association between seaweed and type 2 diabetes? What do I need? What p-value do I need? I need a p-value less than 5%. I need these to be so different that the difference would only occur less than 5% of the time if the null hypothesis was true. That allows me to justify rejecting the null hypothesis. Okay, so now I got to change this into a p-value. So now I'm going to stumble a little bit because I got to remember chi-squared dot dist dot rt parentheses. Yeah, that's it. Okay, and if you look here, it asks for x and degrees of freedom. Okay, so x, if you look up in the help section of Excel, x is actually just the chi-square value. And then comma, it wants degrees of freedom. So what are the degrees of freedom here? The degrees of freedom are the number of rows minus 1 times the number of columns minus 1. There's 2 rows, minus 1 is 1. There's 2 columns, minus 1 is 1. 1 times 1 is 1. So the number of degrees of freedom is equal to 1. I'm going to close parentheses, and it's going to give me the p-value, which is 0.04. In other words, we can reject the null hypothesis because the probability of getting this big a difference produces this chi-square value, which represents a probability of the null hypothesis being true of only 4%. Does that help?
Yeah, that was really helpful. Thank you.
Okay. Now, there's ways for you to do this simply, right? You go to an online calculator, there's a link to it, or you could use R and use just those 2 lines of code should give you what you need out of R.
Yeah, I'm gonna try
this
that.
This is really what, if you did that with already online calculator, you wouldn't actually see what's happening. You just get the answer. But this is what's actually happening. It's not as complicated. Your chi-square, it sounds like going to be a complicated thing, right? It's not really a complicated thing, right? So the only thing that's complicated is the math that converts the chi-square value, the probability theory, the chi-square value into the p-value. That is a bit complicated, but the actual concept of how chi-square is calculated is really pretty simple. It's just 2 tables compared. Okay, so before we tune out, I want to get to these. I want to go over this idea of these tables. Okay, so now let's go to the tables themselves. Let me go to the bright space. We're on bright space, so I can't get back here. I'll go in here this time. Okay, so down at the bottom here, we got project 1. Project 1, part 1. And project 1, part 1, we have a description of what our expectations are for part 1 of this project. In brief, what I'm hoping for here is I'm hoping for you to tell me which of these databases you'd like to work with and which variables in those databases that you'd like to work with. And then also tell me your research question. In other words, if one of these databases had information about whether people had asthma, diabetes, and so on and so forth, but also mentioned, oh, these people eat seafood or they don't eat seaweed or don't eat seaweed, your research question could be the thing we just asked. Is there an association between eating seaweed and type 2 diabetes, either good or bad? Is there an association there? That would be a great research question, right? So, but you need a database that would do that for you. There's one other little complicating factor, and that is that's nice for you to do that. However, we're also asking you to do a simple, doesn't have to be complicated, but to also include a simple linear or logistic regression as part of this. Okay, so what does that mean? That means in this case, which was very convenient, they had diabetes or they didn't have diabetes, right? That's a dichotomous outcome, right? It has 2 possible outcomes, yes or no, right? So with logistic regression, you can calculate an odds ratio. You could, by the way, you could have calculated odds ratio with that 2x2 table we just looked at too. You could calculate an odds ratio. That odds ratio, right, can be calculated using the 2x2 table, or it can be calculated using logistic regression, right? Where the output is the is the odds ratio. The output is the probability of having diabetes versus whether or not you compare to whether or not you eat seaweed or not. So you get on logistic regression gives you an odds ratio. So we're asking you to do one of those. The only thing is that we're asking you to do linear regression odds ratio. If we're a numerical variable, like for instance, number of scores on an exam versus the number of hours that you grade, right? Well, those are both numerical variables. Well, in that case, we'd like you to set up a linear regression. That's one where you take those values, individual values, numerical values for both variables, and you create a line that represents the slope, represents the relationship between the predictor variable and the outcome variable. The outcome being the grade, and the input variable, the predictor variable being the number of hours that you study. So the only thing is in both of those cases, one of the strengths of both of those kinds of analysis is that if there are confounders, other pieces of data, other variables that are present that can skew your results, make your results less accurate, right? Less reliable. With those methods, with just using the chi-square as we didn't consider, could perhaps more women eat seaweed than men eat seaweed. And maybe women tend to have low rates of diabetes just because they're women, just because of their gender, right? So you can see that if we didn't include women as a possible confounder, if we just left that off, the gender off, that it's possible we might not come to the right conclusion about seaweed. What's really protecting people from diabetes might be their gender instead of the seaweed. So with linear regression or logistic regression, we can add in another variable after our primary objective, our primary outcome, to see if that confounder affects the odds ratio for the outcome that we're looking at. So we want you to have a database that you could at least find one possible confounder that you can include in a linear regression or a logistic regression. So it means that you can't work with a database that only has two variables, right? You need something that has other variables, hopefully something that would be a reasonable shot at being a confounder, right? I don't think we have to be too sticky about, what's a reasonable shot at being a confounder, the confounders. Now, last week during our review session, I went over the article that we're reading for Project 1 and for Project 2, excuse me. And I mentioned that there's flaws in that study. It wasn't like the world's best study, but it was a very good outline for how papers are structured. The abstract, the introduction, the statement in the introduction of the primary research question, the organization of the descriptive statistics in a table. They call it table 1. That very frequently you put it into table 1 descriptive statistics. The description of how they handle the data, how they cleaned the data, who they eliminated, who they took out, where they found, how they collected the data, so on and so forth, where the different groups came from. And then they went into their inferential statistics. They did their statistical test to test their question of did hairdressers more likely to get these fertility issues than women in the same age group, perhaps not get them. So yeah, and they did several tests where they compared the groups in terms of whether or not they were more likely to have these outcomes for various within these various groups. And they also performed a regression analysis. And in the regression analysis, they tested it two ways. They did it with just the primary predictors that they were interested in, but they also did an adjusted odds ratio, which included some of the elements, some of the variables they thought that were different between their control group and their experimental group, that were different, such as the average age. I'm shooting off the top of my head. I don't remember for sure if that was the case, or the number of years that they worked, or their smoking. Yes, for sure, their smoking status was different in the two groups, right? So smoking status definitely was a possible confounder because one group indeed smoked more than the other group did. They noticed that when they organized their descriptive statistics. So they included it as a confounder there. So now you have all these different databases that you could work with. Okay, so I'm going to open up this one, for instance, New York City Community Health Survey. I have it in a couple of different formats here. This is as a CSV file because that's easy to import into Excel, but it's also as an Excel spreadsheet. I'm going to click on it. It's just an Excel spreadsheet because it's easy to see. I'm going to download it. And okay, and this is an abbreviated version of it. Is it abbreviated? No, I think it's the full date. No. Yes. No, this is the full database. Okay, so what do we have here? What we have here is and I'm going to see if I can't grab this little bar over here. We have 8,800 people that took this survey. 8,800 people that took this survey. They do this survey every year, right? I can show you on the website where they discuss how they collect the data and so on. So 8,800 people take this survey every year. This is the results from 2019. So if I go back up to the top, you will see that they have the variable names. Well, the first variable is the IDs, the person's ID. This identifies the person so they can preserve their anonymity. And there's another database separate that they don't release that tells them who this person was in case they have to go back and follow up, right? But you don't get to see that. You only get to see their ID number. Okay, and survey. This probably has something to do with either who took the survey or what version of the survey it was. And then you have various others. Weight 20, W20, mood 1, mood 2, mood 3. These are kind of nebulous. Whoops. Yeah. Oh, why is this doing this to me now? Hang on a second here. Let me get this to stop. Okay, that should help. Okay, so, oh no, did I close that? No, I didn't. Good. Okay, so now this is the actual database itself. Okay, so now, but these names, these variable names, they're some of them are easy to understand, like birth sex. In other words, one represents probably female and two represents probably male, or the other way around. Well, that's great, but this is the way the data is stored in this data set. And this is generally the way that it's stored in commercial software. In other words, SAS or SPSS, they would normally code it with a particular number. Okay, so how do we know what that variable, what one represents and what two represents? Well, what we can find out here is that we can go back to our collection of databases. And what I've given you also is I've given you a code book for that data set. So here we go, and 20, survey. I gave you the survey and the code book. So the survey is details on how they ran it. This is literally a script that they use for asking these questions and how they ran the survey. The code book describes how they stored the data, how this data is coded. I'm going to go in here, and this one I'm going to open up. I'm going to download and open up. Oh, maybe if it lets me. Where's download? Why don't I see download? Maybe nope, that's not it. Okay, so let me go back. Code book. Okay, here we go. Okay, now I'm going to open this up. Oh, no. Did it open it? No, didn't open it. Oh. Did it do it now? Nope, still don't have it. I don't know why it's not cooperating. Oh, wait a second. Well, I'll go back to the way we were looking at it here. Because I don't want to kill too much time here doing this. Okay, you should be able to download this. For some reason, it's not cooperating with me right now. Okay, at least we got a little bit better look at this now. Okay, so now if we go through this, the variable names are in here. So Insure 5, Insure 5, let me see if we can go back there. Insure 5 represented, do you have health insurance? If you have health insurance, let me see if the previous page. Insured, this variable is, do you have any type of health insurance? 1 represented yes, 2 represented no, and the rest of these are either didn't know, refused, or is missing data. So those are all things that can be eliminated. So yes or no, that's a simple yes or no answer, right? And then there's more information about that. Do you have any kind of health insurance coverage? Yes or no? What type of health insurance do you have? Employer, self-purchase, Medicare, you have all kinds of data on that. You have health questions. You have, for instance, diabetes. Ever been told by a doctor or a nurse that you have diabetes? So you know 1 is yes, they have diabetes. 2, no, they haven't been told they have diabetes. Ever told you have asthma? Yes or no? And so on and so forth. You have you may remember there was the first few variables that we saw were mood 1, mood 2. Do you feel during the past 30 days how often you feel sad, so on and so forth, all of the times. So we have a categorical variable representing mood, nervousness, fidgety, mood 5. How often do you feel that everything was an effort, so on and so forth. So you have measures of their psychological profile. You have nutritional information here. Birth sex. There we go. We were looking at that. Turns out 1 is male, 2 is female. These others either refused or don't know, for whatever reason, right? So that variable, birth sex, or sometimes originally was called BEMOG 175, identifies that. Now you have ages. I think you actually have a numerical variable for age here somewhere, but you also have categorical variables for age and so on. So you have any number of you have so many variables in here. Stuff on weight, on employment, on type of employment, on where they live, what borough they live in, nutritional questions, sexual behavior, colonoscopy, mammograms, so on and so forth. Weight. There's stuff. I average number of days when you drank. How many drinks did you have? Alcohol consumption. There's other nutritional information here too. So at any rate, you have a plethora of variables that you have here. So with this particular database, it's entirely conceivable that you may not want to you may want to narrow this down to, out of 80 variables, you may only want to use 4 variables from this data set. You're going to need at least 3, right? Because you're going to need at least 1 predictor, 1 outcome, and at least 1 possible confounder. But you might want to use more. You might want to hold on to at least 4 or 5, 6 or something like that. So you have enough. You have enough that maybe you'll find something you'll be able to play with something interesting. So you don't need all the rest of these. Now you can, if you want, you can import this into R and remove and filter out only the variables that you want into a new data set. Or you can just go into here into Excel, delete the ones you don't need, and only leave the ones you do need. and import only those data and only that sub data set into R or into SPSS or into whatever database that you want to use. Now I have set up a couple of, I'm going to be adding another couple of versions of a database that's there already that I just put together. And that is the Community Health Survey. This one is a simplified version. It's from 2013, and it's on there and has only these data sets. It has demographic 1, I believe that's the age of the individual, the borough they live in, their race, their neighborhood, whether or not they're insured, what kind of insurance they have, whether or not they got a flu vaccine, what their gender is, whether they were born in the United States, and I guess whether or not they have children or how many children they have. And these are all numbers here. So you need to know, what do these numbers represent? Well, I want to know what those numbers represent. You need a code book to tell you. And along with this, here's our code book. And the code book, you can look up these various variables. Like, for instance, new race. That one's a complicated one. F, new race. Search it. It's a PDF file. New race. So 1 represents non-Hispanic, 2 represents Black, Hispanic, 3 represents Hispanic, Asian, Pacific Islander, and other non-Hispanic is what those 5 categories for race are. Insured looks like it's dichotomous, right? That we remember what insured is, right? One is insured, one's not insured, I believe, right? And so on. And flu vaccine, we can look that up. Flu vaccine. And 1 represents they got a flu vaccine, 2 represent they didn't get a flu vaccine. So you can create your own subset like this, or you can use the entire, or you can use one of the ones that we've provided. Another one that we've provided, for instance. Yes.
Professor, quick question. Before we move on to the next data set, I was wondering, could potential research question, let's say if I wanted to use this question, this data set that you just showed, the CHS 2013,
Yep.
Could there maybe a potential research question be which demographic traits is most likely to be associated with successful flu vaccinations? Could that be one question?
Yeah, that sounds like a great question. However, I would, it's kind of a broad, kind of like a overbroad question a little bit.
Okay.
Maybe a better way to phrase it would be, is there an association between racial group and the likelihood of getting a flu vaccine?
Okay. So like one particular racial group and
Or
the
no,
flu
or
vaccine.
say, well, you could do all of them for guys. Like, imagine what would be the exposure and the outcome? The exposure would be the racial group.
Yeah.
Outcome would be whether or not they got a
Flu.
vaccine.
Yeah.
So you could do a chi-square, right? And
Mhm.
you could have 5 racial groups, 5 rows, and you
Mhm.
do a chi-square value. The only thing is that you wouldn't have the order of magnitude between the races, right? But
Right.
what you could do then, you could do odds ratio, right?
Mhm.
And the
Mhm.
way that you would do, well, the only problem is that you only do odds ratio for a 2x2 table.
Mhm.
But you can make in a 2x2 table. So you can make the first group your reference group. So
Mhm.
maybe your reference group is white, for instance, right?
Mhm.
Then you can compare row 2 to row 1 and calculate an odds ratio. Row 3 to row 1 and calculate odds ratio. Row 4 to row 1 to calculate odds ratio. Row 5 to row 1 to calculate odds ratio. So you can calculate odds ratios and confidence intervals for the comparison of each group to one, in addition to chi-square. Not only that, but then you could also maybe uh, 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 calculate a confidence interval, excuse me, doing a logistic regression where the output is the probability of having a flu shot and the input is the exposure variable is race. And you remember with different categories, R took the lowest, whatever you defined as one, the lowest alphabetical or number as the first letter. You took that and used it as the reference group. You could change that if you want. It's easier just to change the name of the variable name. So it would take the lowest one, and so it would calculate for you an odds ratio for each comparison. Logistic regression would calculate an odds ratio for each comparison of the other four races to one particular race. So you could use our, in fact, we did that in one of the class exercises. In addition to that, you could then see if you had another variable in that set besides race that is a predictor of, that might also be confounder, which is a predictor of whether or not you get a flu vaccine. For instance, one of the variables was is whether or not they're U.S. born. I'm trying to think of what that's called. There's a name for that. There's a word for that. Starts with a P. Can't think of it. Parity. It'll come to me some other time. But in other words, there was variable in there for one, you're U.S. born, two, you're not U.S. born, right? So it's entirely possible that if you're white, it's more likely that you're U.S. born as opposed to other racial groups, right? That I don't know that that's true, but you could check that, do like a T, like do a T-test like they did in the, you can compare the groups as they did in the Project 2 paper, right? To see which of, whether or not there was really significant difference between different racial groups, whether or not they were born in the United States. So if that perhaps perhaps what's influencing whether or not you're getting a flu shot is not really whether you're white or some other race, but really whether or not you're born in the United States. If you include that as a potential confounder, you can adjust your odds ratio for that potential confounder. You can take that out of the mix as a confounder. So that's great. You have not only do you have, a good way to, good set, a bunch of things that you can do descriptive statistics with, but you also have, you can do a chi-square, you can do odds ratio, and then you can even do a logistic regression if you wanted to. So yeah, if you play around with that, that sounds pretty good to me, actually.
Sounds good. Thank you, Professor.
There's another data set I just wanted to bring up, another data set called North Carolina births. And what I've done here is I've converted it all to numbers in a code book in case you wanted to use SPSS or something like that. The original database looks like this. Let's see if I can get it up. Looks something like this, and with a number of variables. And I made it and this is a code book for that as well. So that's there. But there's a whole bunch of these data sets. So go through them, find one that you feel comfortable with, and the whole point of you may have noticed that it's split. So 5 points for part 1 and 10 points for part 2. It's kind of divided up. But as far as I'm concerned, that the real purpose of part 1 is to have you submit something that we can look at it and then give you feedback to let you know whether we think that it's a workable workable project for you. In other words, that you're not going to paint yourself in the corner and waste a lot of time. So that's really the reason for part 1, is to give you feedback on what you plan on doing. So look through all the different databases and stuff like that. Tinker around with them. See, take that approach to it. Take the approach, I want a simple research question. I don't want a research question that says, for instance, I want to know whether every race has a different rate of getting flu vaccinations based on whether they're in this country or out of this country, whether they're born here or not born here, and if they're insured. And it's give us a really basic research question, and then give us the variables that you want to, the few variables that you want to use to demonstrate that. Okay, don't make it too complicated, but also don't make it too simple. Keep in mind that we're looking for a set of descriptive statistics. We're looking for some inferential statistics, including, just regular chi-square t-test, whatever you wanted to do there. but also including either a linear or logistic regression that includes more than just that one exposure variable that you're most interested in. Okay.
Okay. Thank you so much, Professor. That was super helpful.
Okay, you guys, you other guys that are silent in the background there. Oh, there's a chat here. Hang on a sec. Oh, no problem. Okay. All right, good. So I'll be doing this again next week. And let me see when we say that the due date for now, my own opinion, the due date for part one on project one, I think I put it down as October 20th, which is next Monday. Maybe I'll do a review session on Monday this week. So you have a chance to, like, if you have questions at the last minute.
Oh, Professor, really?
That's a loose due date. I put
Okay.
the due date there because I want to give you guys enough time to actually do the actual
Okay.
project.
Just a quick question, Professor. When do you anticipate part two being due?
Well, it's due already. Oh, part two. Oh, I think there's an announcement that's there. If you look at the announcements, there's a
Oh,
few
oh,
announcements that are there. However, I'll tell you right now, part two, I believe we said that on October 29th, which is the last day, or 30th, the last day of the quantitative portion of the class, session 9,
okay.
you're asked to do a 3 to 5 minute presentation. If you're in the in-person class, you're going to stand up in front of the room and do a 3 to 5 minute presentation on your stuff. You can do a PowerPoint. We'll put it up on the board or something like that. 3 to 5 minutes, not a long time. Real quick, just tell us. It's going to be telling us what you did, right? So you're going to do that, but the actual written paper is not due until the following Wednesday, which is the day before your first the qualitative course. So
Okay.
the overall date is November 6th. 5th, I think. So I'm hoping that you won't wait until that last minute. I mean, for all intents and purposes.
Yeah, of course.
Yeah, for all intents and purposes, you'll probably be done, on the 29th or 30th or whatever it is, because you're going to do that little presentation. But
Right.
the extra time you have it as well. Plus, if you get a little bit of feedback that makes you want to change something, you have that opportunity too. Okay, but
All
there
right.
should be something in announcements. Nobody reads my announcements. You know
Oh,
what?
I'm sorry.
I think I make them too long. They're too wordy. So, and I put up too many of them, so I think they get buried. Okay, and plus I got all the ones pinned at the top that are have to do
I
with.
mean, the announcements are super helpful, though. I just must have missed it. I'm sorry, Professor.
Okay. No, if it's not there, email me. Okay, should be there
Okay.
for details on when these various things are done. But definitely email me if you don't see it there.
Okay. Thank you, Professor. Have a good night.
Take care, guys. The rest of you too that are hiding in the background there. Bye.